Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing about the second module of instrumentation and sensor subject, which is being offered in the civil engineering GTU semester 6. Up until now, we have seen different type of instruments, different type of sensors. We have seen different type of measurement and different ways of uh, install a sensor. We have seen different methods for selection of sensors, and now that we have seen different types of sensors based on their applications that we have seen in the very previous class. If you want to check out that video, you can, by the way, click on the top right hand side corner of your screen in the I button, and it will take you to the previous class video and you can check it out. And this video will be in the continuation of that. Today we are going to discuss about different operating modes of different types of sensors that we have discussed previously. And first operating mode that I'm going to discuss about will be the ultrasonic sensor. And by the way, we have discussed about ultrasonic sensors twice now, in previous chapter videos as well, and very previous video as well. So it has different operating modes and devices configurations enabled microsonic sensors to be used in all conceivable automation applications. It has a blind zone. The ultrasonic sensor has a blind zone which determines the smallest permissible detection range, and no object or disturbing reflector should be placed in the blind zone because it can lead to incorrect measurement for my ultrasonic sensors. And the detection range of ultrasonic sensor is measured by different standard reflectors, and by the way, it holds very short range. It goes for few meters only, so you cannot expect ultrasonic sensor to travel to get a high range application. The operating range is the third range. That range is the sensor's typical area of operation in which it provides you the sense of distance, and this sensor can also be employed for distance up to the maximum range in the case of good reflectors, right? So it depends a lot on what reflectors are being used, and without that it would be difficult. And here we have the German and European standard. If you want to check out, you can check it out. And here you can see different type of modes of ultrasonic sensors, right? First one is something that we call the proximity switch, which tells you the proximity range when the ultrasonic sensor is in the reflective mode. Then we have the window mode, in which we see if switch is activated or not activated, and switch would be activated for very short duration of time unless the proximity switch, right? Then the two-way or reflective ultrasonic barrier that we have. So the switch would be activated until the barrier comes. After the barrier, switch would not be activated. Then we have ultrasonic sensor with analog output. So the there is a sensor that converts the input signal into linear output, right? So it has the analog window present here. Then we have the ultrasonic sensor with IO link or input output link. Then we have the ultrasonic double sheet controllers, in which we have two sheets rather than one. Then we have the through beam barrier, in which the signal has to go through the particular hole in the ultrasonic sheet, so it would only allow a small beam to pass through it, right? Then we have the ultrasonic label and uh, splice sensor. Then we have the ultrasonic edge sensor as well for the detection of an edge. So these were uh, different type of ultrasonic sensors and their operating modes. Now let's see the operating modes in photoelectric sensors here. So photoelectric sensor have five different operating modes. First one is the through, in which the beam is a through beam in which the long distance detection takes place. So as you can see here in this image, this is a through beam detection in which the long distance detection is taking place. See, this one is measuring till here, right? So the long distance detection is taking place. The second operating mode is a diffuse mode, which uses the target reflective properties, right? So here here comes the wheel, and wheel when wheel intersects the particular signal of particular photoelectric sensor, then it would use as a target reflective property. And after that, what happens? We get the diffuse with background suppression, right? So it discriminates between background and the target. It separates background from the target. And what result do we get after that? So the detection of target is done at the same range regardless of the color, right? You get to identify your target. You will be able to tell that this wheel is my target, even though background itself will also be black, right? So as you can see here, that this photoelectric sensor is detecting this wheel as its target, right? It is discriminating between background and the target, and as a result, the target will be separated from the background, right? So it will be able to aim. The fourth operating mode is the reflex operating mode for the opaque targets, which are not transparent, by the way, right? So for opaque targets, like wheel itself is a opaque target, we have the reflex. And the fifth, the polarized reflex, which is used for detecting the shiny objects, right? So for the detection of shining object, as you can see in the fifth one, we use the polarized reflex. So these were the five different operating modes of my photoelectric sensor. Now that we have discussed about photoelectric sensor, we have to discuss about the proximity sensor as well. Different types and modes of operation of proximity sensors. So there are six total different types or styles of proximity sensors. First one is the called ray tube. So the ray tube is the ray type proximity sensor and is ideally suited for simple modeling of a proximity sensor or for modeling of a laser rangefinder. And as you can see, this straight line, this stands for the ray type proximity sensor, right? They are basically the fastest proximity sensors. Then we have the randomized ray type, which are the proximity sensors that operates as a ray type sensors that randomly sweeps a cone volume, right? It randomly sweeps a cone volume. So it has a similar appearance as a cone type proximity sensor. So the randomized ray type uh, would be something that similar to cone type, right? So something that is similar to cone type, but it has not been shown here, so I will not be able to show it to you. Then we have the pyramid type. Pyramid type proximity sensor is ideally suited for simple modeling of a proximity sensor for with a detection volume that is rectangular, right? And pyramid type are also very fast as well, just like the ray type. Not as fast as ray type, but they are fast as well. And this second one with this image is the pyramid type. Then we have the cylinder type, which is ideally suited for simple modeling of proximity sensors with detection of a volume that is revolute. And because they are revoluting volume, they are also very fast. They are required to be very fast. So the third one that you are seeing here is cylinder type. The fourth one is called disk type. So the disk type proximity sensor allows the precisely modeling of proximity sensor with a revolute scanning detection volume, and it is depending on the selected precision and operation mode. That can be little bit more calculation is intensive, right? And the final fifth type is the sixth type is the cone type. It allows for the best and most precise modeling of most proximity sensors, and it depends on selected precision and operation mode as well. So these cone type can be very calculation intensive, and the randomized rate type looks just like this cone type, right? By the way, this is the disk type. So the proximity sensors operate in a geometrically exact manner. So they perform an exact distance calculation between their sensing point. Like for an example, let's take a small sphere and any detectable entity that interferes with its detection volume. Right? I'm repeating again. The proximity sensors operates in a geometrically exact manner. That means they perform an exact distance calculation between their sensing point. Let's say this is the small sphere which is their sensing point, and the detectable entity that interferes with the detection volume, right? So they don't perform a simple collision detection between sensing volume edges like most other simulation software, but they give you an exact distance calculation with the detection of volume as well, right? So what and how the detection takes place in the distance detection takes place in the proximity sensor. So first it will compute sensing from the sensing point till the union of the detectable entity and the detection volume, right? So it will not only if this is my sensing point and if this is my whole object which is required to be detected, then it will not only detect the distance of an object from the sensing point, but it will also detect what volume does it holds. Understanding? So the minimum distance calculation between sensing point and the intersection of detectable entity and detection volume, right? If I've said a union uh, a few minutes ago, then I would ask for your apologies because it is intersection, not union. Sorry. Now, if proximity sensor detects an object, then a trigger is activated, which will result in a call to the trigger callback function. Right? There is something called trigger callback function that we will be understanding in upcoming time. Now that we have discussed about the proximity sensor, I want to discuss about the selection of the sensor and the six things which we shall consider before selecting the sensor, right? So even though the details of evaluation for the selection of the sensor are very different and depending on the type of measurement, that each division will be based on the same basic types of analysis though, right? And obviously it is important to gain familiar with the various sensors or options and trade-offs between them before trying to make an evaluation. So sometimes what happens, many sensor manufacturers will provide you information in advance related to some basic information related to their products that can be used to gain some insight into various options for making measurements. But it is important to make sure to research about options, as sometimes the data will not discuss the methods and not productized productized by the manufacturer, right? So these are the six key items which we shall always consider before selecting a sensor. First one would be accuracy and precision, and we have discussed about that in detail earlier as well. I'm discussing one more time that these two terms are not same. Accuracy has to do with how close the sensor reading is to then to true value, while precision refers to ability of the sensor to detect smallest changes, right? So for an example, a temperature sensor that measuring the boiling water at 97.53 degrees Celsius has high precision but low accuracy, right? Both accuracy and precision of a given instrumentation system must be appropriate uh, for the requirement of that particular system. And too high precision can give false information and impression that the reading is also accurate, or can result in the system detecting noise rather than actual desired data, right? And a sensor with more accuracy than necessary will be more expensive and more difficult to use properly than the one which is more appropriate to the measurement required. So both accuracy and precision are affected by the errors which are incurring in the system, like transducer error, wiring signal condition, gauges or converters which are used to read the valve value or any other values, right? So each and their own errors they have, and these errors into the system that must be understood in order to select the appropriate sensors. The second factor would be the environment. So the selection of the proper sensor requires a good understanding of the environment in which it is going to be operated, and many of the sensors can be affected by non-ideal conditions of production floors like temperature variation, vibration, humidity, chemicals, etc. But it is important to take the environment into account when selecting the sensor and its packaging, mounting, and any and all other options. Then we have the excitation. So many transducers require power to produce an output signal, and it is important to provide a power source that will not introduce additional errors. Then we have the signal conditioning. But electrical noise is always present, uh, and often more so on production floor, and it can cause error erroneous readings. So signal conditioners are other protection circuits that can provide some protection from these effects before conversion, and sometimes they are useful, but other times it is possible to prefer the process signal after conversion, so the use of the condition must be evaluated during the instrument design process. So fifth and sixth are the conversion and the processing. So in modern system it is often preferred that the instrumentation system provides the digital data rather than the analogous gauges or chart recorders. So the analog to digital converter must be evaluated and the matched appropriately to the sensor or error that can be introduced, or the money wasted by overpaying for precision in one that is not present in the other, right? So make sure properly handle the ratio metric and non-ratio metric sensors by properly matching with converters that are same. The final one is the processing. So even if signal conditioning is performed, the sensor and conversion process is full of various sources of error, and some of these errors are linear, some of these are non-linear. Linear means that consists of effect across the measurement values or measurement ranges rather than, while others are non-linear, and there are different methods and algorithms that can be used to compensate for those errors or to extract the best possible signal from them, right? So the data ultimately must be displayed or used by the system and may be stored for later analysis. And whatever is done with that data, always remember this, that a test system can only perform as well as the data that is being provided. So appropriate analysis must be done when selecting and implementing the instrumentation. So that would be it. We will keep today's class till here only. Next time we will be discussing some other important topic. So until next time, thank you very much for listening. If you have any doubts or queries or any questions, please feel free to mention them in the comment section below. If you have any suggestions or feedbacks, please mention them in the comment section below as well. I have noticed the students don't ask question normally, and then in exam it reflects in the results that they have not understood or grasped the concept properly, and they have uh, wrote incorrect answers because of this unclearness. So be a good student, ask as many questions as you want. I would answer them as many as them possible and as quick as possible. Don't be shy to asking the stupid questions or the simple questions. Sometimes the simple questions gives more insight to the faculties itself rather than the difficult questions. So it is important to ask simple questions as well. So we will keep today's class till here. I will be seeing you next time with next lecture. Thank you very much for listening. Till then, take care of yourselves, and goodbye for now.